Now we just learned interval notation and reviewed solving linear inequalities in order for us to have the understanding we need to solve the inequalities with absolute values. This is one of the most critical parts of today's lesson. When solving inequalities with absolute value signs, I want you to first isolate the absolute value expression. I want it to be the absolute value of some expression is less than c, or less than or equal to c, or the absolute value of the expression is greater than or equal to c. Next, I want you to identify if the sign on the opposite side of the absolute value is positive or negative. Just like when we were solving absolute value equations, the positive sign or the negative sign on the other side of the absolute value was very important. It either gave us solutions or it gave us no solution. In this case, again, whether it's positive or if it's negative, we're going to have a very different set of answers. We will not be covering the case where the absolute value of the expression equals 0. It's not covered in our text, so we will be skipping that. We will only be covering the cases where the absolute value is greater than or less than a positive number or greater than or less than a negative number. And I need you to understand that those are very different. First, we're going to explore when c is positive. The next several cases that we'll be looking at all have c being positive. After we do several examples, then we'll come back and do the negative part. But I need you to understand that they're very different. The positive part gives you one set of answers. The negative one will give you an entirely different set of solutions. First, let's look at this inequality. The absolute value of x is less than 2. Now, I know you don't know what the answer is to that right now, but I want you to just kind of think about it in your head. Let's graph the solutions that we do know. Let's label our axes. And what values can I plug in for x that when I take the absolute value of them, I'm getting something less than 2? And usually us students will say 1, because the absolute value of 1 is 1, and we know 1 is less than 2. So I'm just going to put a little dot here. This is just a little exploration activity. The absolute value of 1 is less than 2. The absolute value of 0 is also less than 2. Someone usually gets that one. And then some clever student says, oh, I know. The absolute value of negative 1 is 1. And so that works as well. So usually these are the three that students usually get. Then I ask, hey, is the absolute value of negative 2 less than 2? Well, no, it isn't. The absolute value of 2 is 2, which is not less than 2. But 1.99999, the absolute value of 1.99999 is. So I'm allowed to get really, really, really close to 2, but not equal to 2. The way we denote that is with an open circle. Really, really, really close to 2, but not equal to 2. Similarly, the absolute value of negative 2 is not less than 2. So we're going to have an open circle here. But the absolute value of negative 1, that's a negative 1.9, is less than 2. So I'm allowed to go any value in here. And you can start to see that the interval of solutions is any value between negative 2 and positive 2. And the solution in inequality form would be negative 2 is less than x, which is less than 2. X is now sandwiched between negative 2 and 2. The way we write that in interval notation is negative 2, comma 2. Let's take a look at the next problem. The absolute value of x is now greater than 2. Again, these two look very, very similar, don't they? The only difference is the first one was less than, and the second one is greater than. And you'd think that the solutions would be the same or possibly similar. Well, they're actually very different. Let's label our axes. And then let's start thinking of what value can I plug in for x, such that the absolute value of that x is greater than 2. And my students usually start calling out answers here. Someone usually picks 3. The absolute value of 3, which is greater than 2. And 4, the absolute value of 4 is greater than 5, and so on and so forth. And this keeps going up forever here. Is the absolute value of 2 greater than 2? Well, no. Similarly, with the less than example, we are not allowed to be equal to 2. So we have the interval of answers, all values greater than 2. Is there any other values on this line that also work? And after you think about it for a little bit, some student usually calls out the absolute value of -3, which is 3, is greater than 2. So this one works as well. Similarly, the absolute value of -4 is 4, positive 4, which is greater than 2. And all of these work. And again, goes as large as you want there in the negative direction. Can I be equal to 2? Well, no, again, I can't be equal to it, but -2.1, the absolute value of -2.1 is greater than, so I'm allowed to go all the way right up to 2, but not equal to 2. So notice that my two graphs of solutions are very, very different from each other just by switching that inequality sign. The solution in inequality form for the greater than example is x is less than -2 or x is greater than 2. The solution in interval notation, we have two intervals here, so we're going to connect the two intervals with a union symbol. The first interval is -infinity, it goes left forever, comma -2, I cannot include the endpoints, union with 2 to infinity. So to summarize, if my c is positive, my 2 was positive, the less than symbol gives me one interval of answers. The greater than symbol will give me two intervals of answers. Let's write down a rule. Let x be some algebraic expression and c be a positive number. It's so important that you understand c must be positive. The absolute value of some expression, if it is less than c, then we can use the inequality notation. -c is less than x, which is less than positive c. Whereas if the absolute value of x, or some expression, is greater than c, then we have an inequality form x is greater than c, or x is less than the opposite of c. One way to remember this is when you see the less than symbol, you know that this is going to be a less than problem. A less than problem. We're going to call that an and problem, because my x has to be less than c and it has to be greater than -c at the same time. So that's a less than problem. Going one step further, we can call this a less thanwich, because we are going to sandwich the x between -c and positive c. Now this is a mnemonic device. These are just to try to help you remember which one's which. Less than, remember it's a less thanwich, and we have to sandwich x between c and -c. For the greater than symbol, I want you to remember we're going to be greater. If it's greater, then we know it's an or problem, because x is greater than c or x is less than -c. So the greater problems break up into two inequalities, whereas the less than problems break up into one inequality, one less thanwich inequality. Let's look at some examples. These are very, very simple examples. I already have my x expression isolated on both of the first two examples. Next, I want to identify if c is positive. And in this case, c is positive, so I can use the rules above. This says x is less than 3. 3 is positive, and I'm going to make a less thanwich. The x is going to stay in the middle, the positive 3 is on the right, and the -3 is on the left. And this is actually already solved in inequality form. We would like to now graph and answer in interval notation. To graph, I need to mark at least my endpoints. I have a closed circle on -3 and +3, and all the values in between it. The interval notation answer is -3 to 3. Both of those have brackets. On the next problem, again, my x, or my expression, is already isolated. Then I look at my 4, and 4 is positive, so my c is positive. So that does qualify, and we can use the rules above. The absolute value of x is greater than 4. So I'm going to break up into two equations. I know this is an OR problem. I have x is greater than 4. Notice that that's exactly the same equation. I just took off the bars, and that's one of the equations. The other equations, I'm going to change two things. I'm going to change my inequality symbol, and I'm going to change the sign of 4. That's one way it helps me remember. One of the equations is exactly the same. The other one I have to change both signs. The inequality sign changes and the value sign changes. To graph, I'm going to mark my endpoints. I'm not allowed to include -4, and x has to be less than -4. Or x can be greater than 4, again not including. And I answer all inequalities in interval notation is -infinity, comma -4, not including the -4, union with 4, comma infinity. And that is my interval answer. We have 4 more examples where c is positive before we get to explore where c is negative. Looking at this next one, the absolute value of 3x minus 2 is less than 8. Notice the 3x minus 2, the absolute value is already isolated. I don't have multiply by anything on the outside or add anything on the outside. So then I look, is c positive? And my 8 is positive, so that's good news, and I can use my formulas from above. This is a less than problem, so this is a less than which. My expression 3x minus 2 is going to be the inside of my sandwich. I have a positive 8 on the right and a negative 8 on the left. And I'm going to solve this compound inequality by adding 2 to all three sides and then dividing all sides by 3. My inequality notation answer is -2 is less than x, which is less than 10/3, which I can now graph. One way to graph is just to mark -2 and 10/3 and the endpoints and graph from there. Although some people would reduce 10/3 into mixed form, saying 3 goes into 10 3 times, 3 1/3, and place that between the 3 and the 4, that's also acceptable. I'm not allowed to include the 2, I'm not allowed to include the 10/3, and my x is all the values in between. My interval answer is -2, the lowest point, comma 10/3, the highest point. Again, I'm not allowed to include my endpoint, so I use parentheses. Notice that the next problem looks very similar to the first problem. My expression 3x minus 2, the absolute value, is isolated. Again, my c 8 is positive, so that means I'm good to go. But this is not a less than problem like the first one, it's a greater problem. So I have an or, and I have to break it up into two inequalities. 3x minus 2 is greater than or equal to 8. Notice that's the same equation, just without the bars. And then my expression is going to be less than or equal to -8. Two things changed. My inequality sign changed, and the sign of my 8 also changed. So I have two equations and I can solve them. And I get 3x is less than or equal to -6. Divide by 3. And one of my inequalities is x is less than or equal to -2. Similarly, I'm going to add 2 on the second equation. Then divide by 3. To graph, I have x is less than or equal to -2, which means I have a closed circle because of the equal to symbol, and x is less than, it's to the left. If x is greater than or equal to 10/3, again that's a closed circle, and x is greater than, it's to the right. My interval answer, which is how I want to end all my problems, is -infinity, the low point of the left interval, comma -2, which is the high point of the left interval, bracket, union, the low point of my second interval is 10/3, comma the high point is infinity, a bracket on the 10/3 parentheses on the infinity. And that's my interval notation.